4.2. Okay, so now we're talking about something called the standard normal distribution. So in your normal distribution, what you have is a continuous random variable, and you can also call the normal distribution a bell-shaped curve. But this bell-shaped curve is completely symmetrical. Now the shorthand for writing a normal distribution function is right here. So x is approximately normal, and you've got two parameters. So the first one is mu. Remember, mu is your population mean, and sigma is your population standard deviation. So how you would read this little symbol right here, x is a continuous random variable with a normal distribution. We're going to have three of these. Now, in order to graph this bell-shaped curve like we have right here, you would use this function. But don't worry, we're not going to use it. That's just an FYI right there. Okay? So you have a standard normal distribution. There's two things, actually three things, that are always going to be true about your standard normal distribution. Number one, your mean is always going to be equal to 0, right here. Your standard deviation will be equal to 1. The total area under the density curve, so that's talking about all this area under that curve, that is going to be equal to 1. The reason that it's going to be equal to 1 is we're going to relate the area under this curve to probability. If you remember back in section 5.1, so when we were in section 5.1, we said for continuous distributions, that area is the same thing as probability. And remember, probability only goes between 0 and 1. So the max that it could be is 1. Therefore, the max that the area underneath this curve is going to be 1. Because we're going to really look at probabilities underneath this curve. Now, how you take a normal distribution and you standardize it. So notice all these numbers here, which the number right in the middle of your normal distribution, this is your mean. Then you keep adding your standard deviation over this way, and you keep subtracting your standard deviation this way. Now that is just a normal distribution because your mean is not 0, your standard deviation is not 1. To standardize it, you would have to put each of these numbers, and these are your x values, through this formula right here. Once you do that, then your x values actually turn into z-scores. So all these numbers over here, these would be z-scores. And notice you've got a mean of 0, and you keep adding your standard deviation of 1, or subtracting your standard deviation of 1. Once you have those things, then you say that you have standardized your normal distribution. Okay, now what a z-score will do, it'll tell you how many standard deviations the x value is above or below the mean. And if it's going to be above the mean, it's going to be positive. If it's going to be below the mean, it's going to be negative, like it is here. So I've got below the mean, get it there. If I've got below the mean, I've got negative z-scores. If I'm above the mean, I've got positive z-scores. All right, so here's the first question. So say you've got some thermometers and they're supposed to give a reading of 0 degrees Celsius at the freezing point of water. Tests on a large sample of these instruments reveal that at the freezing point of water, some thermometers give a reading below 0 and some give a reading above 0. Assume that the mean reading is 0 degrees Celsius and a standard deviation of 1. Also assume that the readings are normally distributed. If one thermometer is randomly selected, find the probability that, part A, the thermometer will have a reading of less than 1.58 degrees Celsius. Okay, so number 1, I've got a mean of 0, a standard deviation of 1, and I'm looking at a normal distribution. So the problem is I want a reading of less than 1.58. So we'll say that 1.58 is about here. That'd be 1.58. And I'm looking for less than that number, so I need this area. Okay. So it says, first thing, find the z-score. So, okay, I'm going to take my z-score, which is x minus mu divided by sigma. So that's going to be, the x-score they gave me was 1.58 minus 0 divided by 1. Well, that's the same thing as 1.58. So here, your x values are the same thing as your z-scores. And that was because we already had a mean of 0 and a standard deviation of 1. And those were the things that we needed to have a standardized distribution. Back here, mean of 0 and standard deviation of 1. If we have these things right here, we are already in a standard normal distribution, which means that our x values are really already the z-scores. So what I need to do is I need to find a z-score of 1.58. So we need to go to our z-score table. Okay. Now notice this is the area from the left of the number that they gave us, or the left to the left of the z-score. Okay, our z-score was 1.58. So this chart right here, if I go to 1.58, it's going to give me the area to the left of that z-score, which is what we are looking for. So I need 1.58. So I need to go here first. So I need to skim down to 1.5. And then this is 0. 1, 2, 3, 4, 5, 6, 7, 8. That's the one I need. So if I add this 1.5 plus 0.8, so 1.5 plus 0.08, that will give me 1.58. Okay, so I'm going to stay in this line right here, and where they intersect, okay, there's my area to the left of that z-score. Okay. So the area to the left of this z-score right here is equal to that 0.9429. So that's what our table said. 0.9429. Okay, so that's our answer. Okay. So we said that's the area to the left. But remember, since we are in a normal distribution, that's going to be continuous. So therefore, area is equal to probability. And that's what we're looking for. It says find the probability that the thermometer will have a reading of less than 1.58. So the probability that a thermometer will have a reading of less than, so reading less than 1.58 degrees Celsius, well, that's equal to that area that we just found. 0.9429. And that's our final answer. Okay, so there's 3 cases for finding the probability of a normal distribution, and this is the first case. The second case. So our mean is still 0 and our standard deviation is still 1. So therefore our x values are our z-scores already. So we don't have to put them through this formula here. Okay. So part B, find the probability that a thermometer will have a reading of greater than negative 1.23. So that would be about, we'll say about there, negative 1.23. And we're trying to find a reading of greater than that number. So I'm looking at the area to the right. Okay, so we already said that this is our z-score. So we can go ahead and go to our z-score table. Now as this is positive z-scores, I need to go down to the negative z-scores. And I needed negative 1.2. So negative 1.2. There it is right there. And then 0, 3. So there's 0, 1, 2, 3. If I add negative 1.2, or actually let's just say, if you add 1.2 to 0.03, that will give you 1.23. Okay, so start here. And I go across. Start here, and I come down. Where they intersect, that's going to be my answer. To the left, remember this is always the area to the left of the z-score. Okay, so I have 0.1093. Okay, so that 0.1093, that is to the left of your z-score. So 0.1093. That's not the answer that we're looking for. We're trying to find greater than that number. So I want the area over here. If I know that the total area under this entire curve is 1, I know the area to the left of it's 0.1093, then the area to the right of it's going to be 1 minus what we just found, which would be the same thing as 0.8907. Okay, so the probability that you have a thermometer of greater than, so we'll say x greater than negative 1.23, that is equal to 0.8907. And that is your final answer.